Again, diprotic means 2 protons. Notice the formula is H2S. H2S solution. One of the giveaways here is that there's more than one K value. You're going to see that today in the packet that you're going to work on when I'm done with this problem. When you have more than one hydrogen that can be donated, the second hydrogen is always harder to donate than the first. When you think about it, if you lose one hydrogen, now you're an anion. So you lose an H plus, you become HS minus. To lose a second H plus to something that's already negatively charged is not easy to do. So another giveaway that this is a diprotic problem is you're given more than one K value for this particular thing. So again, like normal, you are given an initial molarity of your acid, and then we can find the pH or the concentrations of everything as well, if we wanted to. So to start this problem, why did I do brackets? I would set up an ice table as I've normally done. And initially I have 0.0250. This will lose X, this will gain X, this will gain X. And then you know the story at equilibrium of 0.205 minus X, X, and X. Now what I can do is products over reactants. So products is X times X, X squared, over 0.0250 minus X equals K1, the first loss of hydrogen. Again, I'm hoping that this all is familiar to us at this point, because again, we're not hanging on to this much longer. We are getting ready to move forward beyond this. Remember that minus X in the denominator is such a small value considering the fact that 0.025 to start with and 9.5 times 10 negative 8 are very different from one another. So we're going to cancel that out. So that gives us a little bit of a shortcut here. So then I would multiply both sides by 0.0250, take the square root of both sides. So I'm not going to show all of that work just to save a little space here. I would tell you that I would get 4.87 times 10 to the negative fifth for my X value. Now, if this were a problem like we've normally done, I could take the negative log of this value and I would get my pH. I could plug it back into my ice table and then figure out what the concentration of H plus is, HS minus, and H2S at equilibrium. However, this is a diprotic acid, which means it has one more hydrogen it could still lose. Because if you look at the formula of this guy right here, it still has one more lead hydrogen. So because of that, there's more hydrogen that can be donated. Therefore, I can't just assume that this 4.187 or 4.87 times 10 negative fifth number is all of my acid ion concentration. I have to do all of this again. Here's the second thing that could act as an acid. Initial concentration of HS minus. Well, if you recall, I solved for X a little while ago. And X happens to be what the HS minus is. So my initial concentration of this is 4.87 times 10 to the negative fifth. So I'm not given initial molarity of it, but I figured it out. Same thing can be said for the H plus concentration. That also is X that I solved for before. 4.87 times 10 to the negative fifth. However, I start off with nothing of the sulfide ion. I change, again, this is going to lose, this is going to gain, which means at equilibrium, I'm going to have 4.87 times 10 to the negative fifth minus x, 4.87 times 10 to the negative fifth plus x, and x. Sorry that I'm kind of getting sloppy here. See if I have enough space to write this a little bit neater here. My other k value, 10 to the negative 19. So, here is my second round. Because if I want to solve for the pH, I need to know the total H+. Not just the H+ from round 1 of losing a proton, but from round 2 of losing a proton as well. However, the reason why I show this, and I believe this is going to pop up as the last question on WebAssign tonight, whenever it's a diprotic acid, the second loss of hydrogen occurs typically at a much more significantly lower rate than the first loss. I can cancel out this plus x and this minus x. That's the shortcut that we've been using for almost 3 weeks now with any equilibrium problem, when the K value is significantly smaller than the molarity. What else can I cancel out now? Come on, calculus people. This, right? It's the same number top and bottom. X equals 1.0 times 10 to the negative 19. Now, if I were to add that to 4.87 times 10 to the negative fifth, it's not going to make much of a difference at all. So in actuality, you probably could have gotten away with doing step number 1 and solving for x right here, and then plugging that into negative log to find the pH. However, the one thing that you would not have been able to solve for very well is this guy right here if you only did one step. But, ladies and gentlemen, you are never going to try to solve for the second conjugate base, the second anion, because I have just shown you the one time you ever need to see this, that second thing's concentration is the exact same thing as the second K. So you will never have to do that math because I've just mathematically shown you that everything cancels out and your X value for this guy right here is that K value. So if you do see a diprotic acid, you still need to do like I did in green, round 1 of our ICE table, products over reactants, you know, what we do with equilibrium. And that can give you most of the information that is asked for. Again, that will give you this value, this value, this value. Once you have the H+, you can solve for the pH. But then if it's asked for the second conjugate base, all you need to realize is, hey, wait a minute, let's look at that second Ka. That is the concentration. Okay? This is actually a continuation from the notes that I gave you last time. But what we have to do to wrap up Ka, and you're going to see percent ionization on your WebAssign as well, is go over what percent ionization means and how to calculate it. Remember an acid. And again, the simplest formula for an acid would be HA, like I've shown in this bottom equation. Sorry, this should be division that's shown here. It's just spacing got a little weird. An acid is neutral to start with. However, when it donates that H plus is an ion. So when we ask for percent ionization, what we're asking for is how much H plus did that original HA create. I've shown that written two different ways up here on the smartboard. Percent ionization is the ionized acid concentration at equilibrium divided by the initial acid concentration, or the H plus concentration divided by the HA. However, that HA in the bottom is not at equilibrium, it's initially. Because we're looking at how much of that initial acid turned into the acid ion. This would give us a percent. Weak acids have a low percent ionization, which makes sense because they don't donate much of their H plus. Strong acids, their percent ionization is getting close to 100% because it almost completely dissociates. It completely donates that H plus. So if we have the concentration of the H plus and the concentration initially of the HA, we can figure this out. Now let's think about this mathematically. What if I don't? Well, just like on the web assign last time, if I gave you the pH, you can know the H plus concentration. Quite frankly, we gave you the K value and the initial molarity. You can calculate the H plus concentration. So there's more than one way that you can actually figure this out. And I'll actually just show you. Didn't want to get on this. An example from what we did on that WebAssign problem that's up on the whiteboard. So up on the whiteboard, we solved for the H plus using pH was 10 to the negative fourth. If I were to take that divided by the original HA concentration that was given to me in that WebAssign problem, multiplied by 100, that would tell me percentage how much of that acid was ionized. Which in this particular problem with 2 sig digs is 0.030%. And it's typically going to be a small value. 5% I would even consider to be fairly small. But that's all that last calculation is. Now, you combine it with what we did last time with Ka. Because typically what you're going to be given is, like on the whiteboard, an initial molarity of something. Now, if we give you the Ka value, x squared over, equals Ka, you solve for x, and then you can plug it in to solve for percent ionization. Or, again, we give you the pH instead. Well, you can solve for the H plus, you have that. So this is just kind of one more step on that math you already did. Because on the way in, you did pick up a sheet that is just, I believe, 3% ionization problems on its own, where you could figure this out. You could do this for an acid, you could do this for a base. If it was for a base, it'd be the hydroxide concentration at equilibrium divided by the initial molarity of the base. So it'd be the same type of steps that you would perform either way that you were doing it. So not meant to be a long explanation. This is just one last thing that I want to tack on to our math. Because the good news is this covers our equilibrium math for a while. There's a couple other calculation things that we still have to do in this unit, but I don't need to tack on really much further when it comes to equilibrium math.